Okay, so up until this point, I've shown you some structures. For the most part, I've told you whether they're chiral or not, but you're going to have to know how to do that on your own. So be able to look at a structure and determine whether it's chiral or achiral. So let's practice that. The first thing you're going to look at is, does the molecule have asymmetric carbons? So look at that first. If it has one asymmetric carbon, it is chiral, and you're done. If it has more than one asymmetric carbon, remember, it may or may not be chiral. Okay, so the next thing you would do is to check if it's superimposable on its mirror image. Okay, now, if you have just one asymmetric carbon, you already know it's chiral, and you're out of there. You don't have to do anything else. But if it has more than one, that's where you might want to check the mirror image, or where you'll need to check the mirror image. If it's superimposable on its mirror image, then it's an achiral molecule. If it's non-superimposable on its mirror image, then it's chiral. And finally, you can look for, although you don't have to, you're going to be able to determine whether something is chiral using the first two things. Does it contain asymmetric carbons, and is it superimposable on its mirror image? That's going to get you the answer. But what you might also want to look for is there internal symmetry? If there is no internal symmetry, remember, that's a chiral molecule. If there is internal symmetry, and what we're talking about here are internal symmetry planes, then it's an achiral molecule. Okay, so let's just start working on some examples. So let's look at this original structure, and I'm going to go ahead and number carbons. So we have some points of reference. And so what we notice with this is that carbons 2 and 4 are asymmetric carbons. So C2 and C4 are asymmetric carbons. And so now we're along the road of it has more than one asymmetric carbon, so it may or may not be chiral. So now we're going to have to test for the superimposability of the mirror image. So let's draw the mirror image. Now we can draw the mirror image in the ways that I showed you previously, either by just drawing it, which is what we're going to do here. So that blue dashed line, that's a mirror plane. And I'm just going to draw the reflection of it on the other side. Okay, so this is our mirror image. Okay, if you pick up the mirror image, so just imagine that you could just lift it out of the page, and without turning it over or flipping it or doing anything, you just lift it up, you move it to the left, and you drop it on top of the one on the left. So you're testing for superimposability here. So here's our original. And then what I'm going to do is just draw this in a different color. I'm going to try to superimpose the mirror image on top of it. Now I'm going to offset them a little bit so you can see what's going on. Okay, so the carbon backbones line up perfectly. They superimpose, they overlay on each other completely appropriately. But it's the positions of the OH groups that don't. Okay, so at this carbon here that I've highlighted in each structure, in one, the OH is coming forward, and the other one is going back, so those don't match up spatially. And the same thing is true at the other carbon that has OH groups. Okay, so that doesn't match up. But remember, you can move the mirror image, or the original molecule, you can move each of the molecules around in space in whatever ways you want to try to get them to superimpose on each other, or to try to check for that. So what we can do next, maybe with the mirror image, is flip it over horizontally. So imagine that you just take a spatula and you put it underneath that mirror image along the paper as if it were a pancake. Pancakes. I think we should plan to have pancakes after we get through with this video. Anyway, you flip this over like a pancake horizontally. So I'm going to put some different labels. Let's call this A, B, C, D, and E. When you flip this over, what that's going to do is A is going to come to the right, and E is going to go to the left. At carbon B, the OH group was going back, but once you flip it over, it's going to come forward. And at carbon D, that OH group was coming forward. When you flip the whole molecule over, it's going to go back. Okay, so as you can see, what you end up with is really the same thing you started with. We've already seen that that's not superimposable. There are no other ways to flip the molecule in space to try to reasonably test its superimposability with the original. So what we can say, what we can conclude here, is that the mirror image is non-superimposable on the original. Okay, so this is a pair of non-superimposable mirror images which we know by definition are enantiomers, which tells us that the original structure, remember the whole point of the exercise was to determine whether the original structure was chiral or achiral. Because it has a non-superimposable mirror image, it is chiral. The mirror image is its enantiomer and is also chiral. Let's do another one. So this one might seem super easy because there's no stereochemistry shown. Instead, what this is what's called a constitution. The constitution is like a Lewis structure without any stereochemistry. It shows the connectivity of the atoms, so it shows the basic structure, but it doesn't show stereochemistry. So it doesn't show any wedges or dashes. So wedge or dash. Let's number carbons. Okay, now at the top of the page, remember the first thing that we're going to do is check to see, does it have any asymmetric carbons? And using what we know about the skeletal structures, we know at carbon 2, there's a hydrogen attached that's not shown, which means that carbon 2 has a methyl group, it has a hydrogen, it has an OH group, and it has an ethyl group. So it has 4 different groups. So it is an asymmetric carbon. Carbons 1, 3, and 4, however, each of those carbons have at least 2 hydrogens. So none of them have 4 different groups. So there's only one asymmetric carbon in this structure. So what we can say then is that because there's only one asymmetric carbon, in this structure, the structure does represent a chiral molecule. It just doesn't specify which enantiomer. Okay, what that means is that it's not telling you if you have this or this. So we would say that that is a chiral molecule. So the correct answer here is yes, this is chiral. However, a structure drawn like this can also, if it's not showing any stereochemistry, represent that you have both enantiomers, but you have exactly the same amount of each. So it may also, the structure may also, when drawn without stereochemistry, represent what's called an equimolar. So the same number of moles of each, an equimolar mixture of the two enantiomers. And this has a special name. It's called a racemic mixture. So that's another way that you can interpret a drawing like this one. Let's do some more. All right, so for this structure, again, what we're trying to do is determine if it's chiral or achiral. Let's start by numbering carbons. So we have points of reference. And if we assess, what we're going to find out is that C2 and C3 are asymmetric. So these are asymmetric carbons. So we have more than one. So now we have to do a superimposability test to figure out if this is a chiral molecule or not. So let's go ahead and draw the mirror image by drawing the reflection of the molecule, just as we did in the previous video. And this time what I'm going to do, so this is the mirror image. This time what I'm going to do is flip this guy vertically. So let's put some labels on things. Okay, so when we flip this vertically, what that does is that it changes the zigzag nature of the carbon backbone. So that's one thing. Notice how that happened. The other thing is that at carbon B, that OH that was coming back, since we're flipping the entire molecule over, will now come forward. And at carbon C, the one that's coming forward in the original mirror image is now going back. If we pick this structure up, the one we just finished with, if we pick it up, lift it out of the page, and then plop it down on the original pre-printed structure at the far left, we can see that it's superimposable. So the mirror image is superimposable on the original structure. And as a side note, we could say all three of these drawings or all three of these pictures are the same molecule. They're all identical. Okay, so the mirror image is superimposable on the original structure. What that tells us is that the original structure is achiral. Now to go back to our previous video, if this is an achiral molecule, then we would expect that is going to have an internal plane of symmetry. But you can't really see an internal plane of symmetry when the molecule's in this conformation. So what we would need to do would be to put it into a different conformation that shows the internal symmetry plane. So we're going to go through an exercise of doing that by using Newman projections to go from one conformation of a molecule to another one. So I'm going to redraw the molecule here. This is our original molecule. And because I want to do a Newman projection, I'm going to include the hydrogens attached at each of those asymmetric carbons. Okay, so we're going to draw a Newman projection. From this perspective. So we're going to look down the carbon-2, carbon-3 bond. And what we can see right away is that the molecule is presently in a staggered conformation. What we're looking for is the most symmetric conformation. That's the one that's going to show us the symmetry plane, the internal symmetry plane. The most symmetric conformation will be an eclipse conformation. So that's true for any molecule. Okay, let's draw a Newman projection of this. Okay, so from your point of view, over on the left, imagine yourself, and you may want to do this with models, imagine yourself now in the plane of the paper looking down C2, C3, which means that C2 is the front carbon, and so from your perspective, the methyl group number 1 is pointing straight down in front of you. You're in the plane now on the left side of that molecule, so the OH group is pointing to your right, and the H is pointing to your left. So that's carbon 2. Carbon 3 is the circle, that's the back carbon. Coming off of the back carbon, pointing straight up, is the methyl group 4. Down and to your left is the OH group, and down and to your right is hydrogen. Let's add in some methyl labels to all of these so that we don't get messed up. Okay, now the reason for doing the Newman projection is that it's easy to look at a wedge and dash structure like the one that we have on the left, and then just mentally imagine rotating around a bond and trying to imagine what you end up seeing. What's the resulting spatial arrangement of the groups? The problem with doing that is that it's really easy to make mistakes. The surefire way to do this, the foolproof way to do this, is with Newman projections, and so that's why we're doing this. So it's very handy to be able to go from a Newman projection to a wedge and dash, or back the other way. Okay, so what I'm going to do in this instance is keep the back groups the same, but I'm going to rotate the front groups. And what I'm looking for is to get this molecule into the most symmetric conformation that I can. And so that's going to be the one where groups on the front carbon align with identical groups on the back carbon. So as you rotate around, what you're trying to figure out is, can that happen based on the existing spatial arrangement of the groups? And as it turns out, yes, it can. Now, if any of those groups were in different positions, say we had the OH where the CH3 is on the front carbon and vice versa, then they wouldn't line up. But because of the nature of this compound, they do. So now, let's redraw this as a wedge and dash picture. Okay, so now you're looking at the molecule this way. And let's say that this blue dashed line is the plane of the paper or board. From your new point of view, the molecule looks like the following. So carbon 2 is on your left, and carbon 3 is on your right. And now you're actually able to see the bond between them because you're standing on the side of the Newman projection. The methyl groups, carbons 1 and 2, are in the plane. I'm sorry, carbons 1 and 4 rather. Coming toward you at carbon 2 is a hydrogen. And coming toward you at carbon 3 is another hydrogen. And then at carbon 2, going back, is an OH group. And you have the same thing at carbon 3. Now that the molecule is in its most symmetric conformation, it's easier to see your internal symmetry plane. So this is your internal symmetry plane. And so what we have here is what's called a meso compound. So we'll look at meso compounds in a little more detail a bit later. But for now, we can define a meso compound as an achiral molecule, like this one, that has asymmetric carbons. So this is not only achiral, let's go back up here to the upper left, it is achiral and meso. And we can add that in to its descriptor now that we know what a meso compound is. Okay, so just remember what we're trying to do here is look at these structures and figure out if they're chiral or not. We were able to do that by the superimposability test. Okay, so we answered the question. We know that the original molecule is achiral. We also know that because it has asymmetric carbons, that it has to be what's called a meso compound, which is an achiral molecule with asymmetric carbons. We did not have to prove to ourselves that there was an internal plane of symmetry in one of the conformations of this molecule. I did that just to show you how you would go from a wedge and dash structure to a Newman projection, and then from a Newman projection back to a wedge and dash structure, because that can be helpful at certain instances. Okay, but it was not essential to answer the question. Okay, let's do 2 more of these, and then we'll be done with this. So let's take a look at this first one. Okay, I'm going to number the carbons. And let's start by determining if there are any asymmetric carbons. Now this is really a lot like the situation we saw with the dimethyl cyclohexane earlier. It would be these 2 carbons you could suspect of being asymmetric, but neither one of them has 4 different groups, because as you trace around the ring from either one of them, you get to the same place. So just like we saw with the dimethyl, the 1,4-dimethyl cyclohexane example, there are no asymmetric carbons, which means that we're going to have to do a little more work. So let's go ahead and draw the mirror image. like so. So we're drawing the mirror image so that we can test for superimposability. So the question now is, can you pick up the structure on the right, the mirror image, and lift it up out of the paper and then just plop it down on our original structure and have everything match up? The answer is yes, you can. This turns out to be a superimposable mirror image. And the reason for this is the following. You can see that I can imagine that some of you might be a little distressed because of that double bond up at the top. And you might be thinking, well, it's pointing to the left in the original structure, but it's pointing to the right in the new structure. Remember, though, that the bond that stems from carbon 1 on the ring and ends in that double bond is a single bond. So it's constantly rotating. You have constant rotation going around that bond all the time, which means that what's at the top of it, if I can use some artistic license, is really just a blur in both cases. The same is true for the bond to the methyl group at the bottom. There's rotation around that bond as well, meaning that those 3 hydrogens at the end of that bond, attached to that carbon at the end of that bond, are spinning around, and that's also a blur, which means that you have a symmetry plane. So I'll just draw this on the original molecule. There's a symmetry plane that cuts the molecule in half and reflects the left side into the right side. Remember, we can cut groups in half and reflect the left half of the group into the right side. So there is a symmetry plane. The mirror image is superimposable, which means that this molecule is achiral, but it's not achiral in meso because we have no asymmetric carbons. Okay, let's do one more example. Okay, so let's number carbons. Now, once again, we might suspect carbons 1 and 4 being asymmetric, but they're not going to be asymmetric per se, depending or using the definition. Actually, carbon 1 we wouldn't even suspect, because that one is an sp2 carbon. So that's not an asymmetric carbon right out of the gate. But carbon 4 we might think could be an asymmetric carbon, but as we trace around the ring in both directions from it, we end up at carbon 1. We end up at the same place, and so we have no asymmetric carbons here. Let's draw the mirror image. Okay, if you pick up the mirror image, pick it up out of the paper, move it to the left, and drop it on the original, it does not superimpose. That's because this methyl group and this methyl group are in different positions. The difference between this example and the previous example is that there's no rotation around the double bond. And so the position of that methyl group that's attached to the double bond is unchanging. Okay, so as drawn, the mirror image is not superimposable. Let's flip it over. When we flip it over, that methyl group up at the very top is going to come to the left, and the methyl group at the bottom, because we're flipping the entire molecule over, is going to go back. If we then pick this up and try to place it on the original molecule, the double bond and the methyl group do match up now, as does the ring, but the methyl group at the bottom of the molecule no longer matches up. And so what we have is a non-superimposable mirror image. which means that the original structure is chiral. Now, it's a chiral molecule that has no asymmetric carbons. These are not that unusual, but they will be for what we're doing. So I wanted to show you an example of something that was chiral that didn't have asymmetric carbons. So this one is chiral. Even though it has no asymmetric carbons, but it does have stereocenters. So carbon 4, for example, is a stereocenter, as is the carbon up here that I've denoted with an arrow in the original structure. So it has stereocenters, just no asymmetric carbons. So such a molecule can still be chiral. Your focus, though, should be on looking for those asymmetric carbons. That's where we're going to put most of our effort. Okay, one more thing. When we talk about rotation around bonds that are coming off of rings, for example, the preceding structure. I'm going to blow this up a little bit so we can focus in on it. Okay, when this, and you might want to make a model to prove this to yourself. Let's look at the methyl group at the bottom. Okay, so this guy over here. As the bond to the methyl group, the one that's coming towards us, rotates, at no time does it suddenly bust a move and then swing to become a down bond. So right now, it's up. Okay, we know that by the convention, that a wedge coming off of a ring means that that's up relative to the plane through the ring, and a dash bond coming off of a ring means that that's going down. Okay, so that bond is fixed to go up. It's not going to suddenly go back just because it's rotating. So the bond does not change to a down bond because of that rotation. Make a model of this. Make a model of a cyclohexane, put a group on it, make the group come out from your perspective, and then rotate around that bond to prove to yourself that the rotation around the bond does not change the orientation of the bond from up to down or vice versa.